If you are managing a major capital project today, I'm talking about, say, a high-rise residential tower, a massive data center, or even critical public infrastructure like a metro viaduct, the single biggest risk you face, the one that probably keeps you up at night, is integration failure.
Right.
We're talking about that gap between the brilliant design and the often painful reality of construction.
And that gap almost always translates into unexpected delays and, of course, budget overruns.
Exactly. So today we're doing a deep dive into the blueprint for success. We're going to extract the systematic methodology used by major engineering firms, specifically J&F India, to deliver these huge complex projects.
From the very beginning to the very end.
From concept to commissioning, we've got sources detailing a really impressive history, 25 years of global experience, over 400 specialized engineers, and more than 1,000 successful projects worldwide.
A huge track record.
It is. And our mission here is to dissect the system that underpins their core philosophy, which is more quality, in time, great prices. The real question is, how do they actually get from that promise to a tangible result?
Well, I think it's all about designing a process that is, robust enough to handle radically different markets.
So it can't be a one-size-fits-all approach.
Not at all. The system can't just be optimized for, say, hospitals and clinics. It has to be adaptable for next-generation power infrastructure, too.
Okay, so give us a sense of that range.
Well, think about the breadth here. They're applying this methodology to the energy transition. We're talking renewable energy systems and massive BSS.
BSS, right, battery energy storage systems.
Exactly, which are now absolutely crucial for grid stability. Then you look at the more traditional, highly complex areas like thermal power plants, high-speed highways, and airports.
Wow. Okay, that requires maximum flexibility and, I'd imagine, maximum rigor.
That adaptability is the key differentiator. You can't just reuse the same design, but you must reuse the same high-standard process.
I see.
Yeah, the foundational concept here is synthesizing world-class structural and MEP expertise.
MEP being mechanical, electrical, and plumbing.
Correct. So you take that global expertise and you combine it with this really granular knowledge of local building codes and regulations.
Okay, so that's the key combination. Global standards, local rules.
You need that global benchmark for quality, absolutely. But if you don't know the specific fire egress requirements in Kolkata or the seismic codes in Istanbul...
The project fails before you've even broken ground.
Precisely. And crucially, this entire framework is built on a foundation of BIM-enabled or building information modeling workflows.
Right. And we've broken this whole process down into 5 systematic phases. By understanding these steps, you're essentially getting a shortcut to seeing how they reduce project risk.
It's the difference between a project that requires constant firefighting and one that just runs smoothly.
Delivering timeline control and maximizing stakeholder visibility. So let's start at the absolute beginning. The point that determines if the project deserves to exist. We're combining the first 2 phases, viability studies and conceptual design. What happens in phase 1, and why is this stage so critical for not starting a project that's destined for financial trouble?
Phase 1, preliminary and feasibility studies, is basically the economic and regulatory gate.
The gatekeeper.
Exactly. This stage is absolutely critical because it provides the data necessary to recommend killing the project if the constraints are just too high. It's cheap insurance.
So what are they actually looking at?
The team executes detailed site assessments, looking at soil composition, access logistics, environmental concerns. They do thorough regulatory compliance reviews and preliminary structural and MEP needs analysis.
But the real heavy lifting is the money side.
That's where the heaviest weight is. The comprehensive cost estimation and risk assessment. They're calculating the internal rate of return, potential economic headwinds, and modeling the potential exposure to unforeseen risks.
So if the regulatory hurdles are too high, or the cost-benefit analysis just doesn't add up, the system is designed to stop investment right here.
Right here, rather than later when your sunk costs are already massive.
It's a filter.
It's evaluating the technical, economic, and regulatory perspectives before you commit significant capital. And once that viability is established, a project moves seamlessly into phase 2, project conceptualization and tender design support.
Okay, so tell us about that transition. How does a favorable feasibility study translate into designs that are ready for bidding?
This is where they solidify the conceptual designs, develop those essential preliminary drawings, and this is key, prepare detailed documentation for competitive bidding, the tender package.
And since they work globally, That has to be standardized.
It has to meet the highest international standards, ensuring clarity and consistency across all contractors who might bid on the work.
Right.
It's the transition from, is this possible and profitable, to, here's the exact scope we require, and this is how we ensure bidders are comparing apples to apples.
Not just locally, but on an international stage.
Exactly.
That standardization is crucial for quality control later on. Okay, so moving past the conceptual gates, we hit phase 3, detailed design engineering. This is where the real engineering firepower comes in, right?
This is the core engine room.
But the big challenge must be coordination.
Absolutely. You have these multidisciplinary teams, structural engineers focusing on stability, mechanical on HVAC, electrical on power distribution, plumbing on water and waste. The central challenge is integration.
Can you give us an example?
Sure. Imagine you are designing a complex data center. You need massive structural integrity for heavy equipment, but you also need acoustic isolation, incredibly robust cooling systems, redundant electrical pathways.
And everything affects everything else.
Every single choice one team makes impacts the others. If the structural team places a main column, it directly impacts the duct routing for the mechanical team.
So the goal in phase 3 isn't just to make the building stand up.
No, it's to integrate every system so they work harmoniously and meet those really stringent performance requirements.
Whether it's power efficiency in a BES facility or, say, patient flow in a new hospital.
Absolutely. The focus is on optimization and constructability. If the design isn't easy and safe to build, phase 3 has failed.
So they're constantly checking in.
This is why regular design reviews and coordination meetings are logged and systematized. It ensures every element, from the size of a riser to where a generator is placed, is optimized for both cost and function.
Which brings us to phase 4. And this is where the conversation shifts entirely into the digital realm, digital engineering solutions. We hear about BIM constantly, but how does this firm leverage it to fundamentally change a project's risk profile?
BIM, Building Information Modeling, is the essential weapon against risk in modern construction. It's not just a 3D model anymore. It is a repository of information.
Information you can analyze.
Exactly. You can do analysis, coordination, and planning that goes far beyond just the physical shape of the building.
What are the tools they're using?
The main ones are Revit for modeling, Navisworks for coordination, and then specialized tools like CostX and even proprietary AI-assisted systems. They're all designed to pull data from a single source of truth.
Okay, and this is where we need to clearly define that leap into 4D and 5D modeling.
Yeah.
We get 3D, that's space. What happens when you introduce the 4th and 5th dimensions?
So 4D integrates time.
The schedule.
Right, the schedule. It means the model isn't static. You can visually simulate the entire construction sequence, milestone by milestone. This is critical for logistics planning and for finding bottlenecks before they happen.
And 5D.
5D integrates cost. Every element in the model, every pipe, every beam, every light fixture is tied to precise quantities and associated costs.
So you get real-time budget tracking.
And procurement planning. This level of accuracy is what feeds the great prices part of their promise.
The ultimate payoff of that digital integration has to be clash detection. This is where the real money is saved, isn't it?
Without a doubt. If you are building a massive tower and the electrical conduits modeled by one team intersect the structural steel modeled by another, that's a clash.
And finding that on-site is a disaster.
It means stopping work, calling in multiple trades, maybe demolishing finished work, issuing change orders. It costs thousands, sometimes millions.
But doing it in the Navisworks digitally.
It costs almost nothing. The real insight here is that fixing a digital conflict costs a fraction of a percent of fixing that same conflict when the concrete has already set.
That is the single biggest reduction in rework and delays.
It is.
And linking that 5D capability back to the budget with tools like CostX and Revit for accurate quantity takeoffs, that means less guesswork in procurement.
You know exactly how many meters of cable or tons of rebar you need. It's a closed-loop system for budgeting that dramatically improves cost control.
I think we saw this in one of the client success stories, right?
We did a complex development with a hotel, a residential tower, and a podium complex.
That just sounds like a coordination nightmare.
It was, particularly because the designs were constantly evolving. But the team successfully delivered all the complex MEP quantity extraction within 8 weeks.
8 weeks, while the design was changing.
Yes. They could maintain that accuracy and quality because the digital model was managing the evolving geometry and instantly updating the cost and quantity output.
That digital agility is everything.
It's the key to managing high-pressure evolving scopes.
That is remarkable. Okay, so we've fully designed and modeled the building digitally. Phase 5 takes us back to the real world, construction and commissioning, but with a digital guide.
Phase 5 is all about execution control. It covers construction administration, continuous quality assurance, and progress monitoring.
And the model is the guide.
The digital model supports the physical build by serving as the verified specification. A huge part of this is handling RFIs.
Request for information.
Right. Formal queries from the contractor to the design team. Fast, accurate RFI responses are essential for keeping the schedule moving. The design team has to stay aligned with the approved digital specs throughout the entire build.
And then the final non-negotiable step before handover is commissioning. How rigorous is that final check?
Commissioning is the ultimate stress test. It's the systematic verification that all the integrated systems, especially the complex MEP and control systems, operate precisely according to the design.
So for a data center, for example.
It means verifying cooling redundancy and power switchovers under a simulated load. For a hospital, it means making sure critical air handling and isolation systems function perfectly.
It's the ultimate quality check before the client takes the keys.
Exactly.
And speaking of quality, the foundation here isn't just the methodology, it's certified standardization. The source material mentions specific ISO certifications. Why do those matter to you, the listener?
They matter because they ensure consistency. It doesn't matter where the project is or which specific engineering team is on it. The ISO 9701.201 FAN certification for quality management means every step we've discussed.
From phase 1 to phase 5.
Adheres to a uniform, auditable standard of quality.
And there was another one.
Even more critical today is ISO 14001.20140, which governs environmental management systems. This isn't just a badge. It legally requires the organization to track, model, and mitigate the environmental impact of the project from day one.
Which is a massive concern for modern infrastructure.
Especially in high-profile areas like renewable energy and green buildings.
The integration of those global standards with this cutting-edge technology, that seems to be where the true advantage lies. We're talking about AI-based systems here, right?
Yes, that is the definition of a technological advantage. They are using proprietary AI-based project and quality management systems.
So what does that actually let them do?
This capability lets the team do much more than just track progress. They can execute scenario simulation in real time, which enables highly proactive decision-making and risk mitigation.
Okay, so instead of waiting for a quality control report at the end of the week,
the AI can potentially ingest data from the model and from the site and flag an issue before it even escalates.
oh,
Precisely. The AI-assisted quality control system can analyze potential issues, compare current progress against the 4D model, and recommend corrective actions proactively.
it's a fundamental shift.
It is. That transition from being reactive inspectors to proactive predictors is fundamentally changing project management.
So to synthesize what we've unpacked, the core takeaway is that this systematic 5-phase process and the technology stack BIM, 4D, 5D, and AI, they're just inextricably linked.
They are.
And that pairing gives them the control and visibility they need to manage these highly complex, large-scale projects globally.
And this scale is only possible because they back that system up with the human capital, over 400 engineers, multiple technical offices, and the ability to offer 247 support across time zones.
The resources have to be there.
That resource commitment is what allows the methodology to successfully manage massive projects at the same time while still maintaining those incredibly tight delivery windows.
Like the 8-week MEP extraction we talked about.
Exactly.
That deep visibility and control is the ultimate payoff for understanding and adopting this integrated framework. And that leads us to our final thought. We've established that sophisticated digital engineering solutions can simulate projects. The 4D and 5D modeling and AI can predict quality issues before they even impact the physical site.
Yeah.
So consider this. If the sophisticated tools of prediction are moving quality control away from the physical job site and into the digital realm,
Yeah.
how fundamentally will this shift the job profile of a traditional on-site quality manager in the next 5 years?
It's a great question.
What new skills will be required to manage these digital workflows and transition from being an inspector who finds problems to a proactive predictor who prevents them? That's the challenge for the next generation of engineers embracing this digital deep dive.